Hello and welcome to another physics lesson with Mr. Mikulski. Today we're looking at our unit on kinematics, and in the Google slide presentation, slide 38 posed a challenge question. The question was for us to create our own formula or an expression to find the displacement of an object after it has accelerated at 5 meters per second squared from rest for 10 seconds. So I'm going to go ahead and walk you through this. Hopefully this is a repeat from what you've done in person with me, but this would be a good way to review and refresh on the concepts that we covered in class. Okay, let's begin. So what I want to do is go ahead and think about what are all of the formulas and pieces of information that were given in the notes. So first equation that I remember seeing was this one. Delta x equals x minus x naught, or x initial. This could have been found on slide 8. We were also given on slide 20 that speed is equal to distance divided by time. On slide 25, we were actually given two things, so we're going to write both of them. One was the v with the line over it. The v with the line over it just means v average, or average velocity, and that's equal to our displacement, delta x, over our change in time, delta t, which could also be written as x minus x naught over t minus t naught. Now, typically, this t naught is equal to 0, so that goes away. And we're left with just dividing by t. The other formula given also on slide 25 is another way to solve for v average. So both of them are valid, just sometimes we use one, sometimes we use the other. And this is saying that our v final plus our v initial, v again for velocity, is added together and divided by 2. And this only applies when your acceleration is constant. And then the final equation that we were given so far is on slide 32, and that was a for acceleration is equal to a change in velocity over time. Again, this is technically a change in time, kind of like up here from slide 25, but if that initial time is 0, all we care about is how much time went by. So if 10 seconds went by, t is 10. Doesn't matter when it started, when it ended, just the fact that 10 seconds have elapsed. Okay, we can rewrite this, saying that v final minus v initial is divided by t is equal to our acceleration. So there are all of our equations. Okay. The next step we want to do is evaluate how do we solve this problem. So I want to come up with some relationship that connects the variables. So here we'll write a little note. It's our goal. We want to connect delta x, our displacement, and we're given an acceleration, so we're going to connect that with an acceleration. We know that it starts at rest, so that's a v initial, and we're given a time of 10 seconds, t. That's what we really want to do. The other piece that's not given here, but just to be complete, is that we have one other variable, and that's the final velocity v. But for this particular problem, we don't know what it is, so we're going to try to see if we can avoid that. Okay. How can we do this? So what I like to think through is start with what we know and keep working through the unknowns until you run out of things that are unknown. And eventually you'll come back to where you started with all of the values that you're looking for. What do I mean by that? What I'm going to start with is I know I want delta x equaling something. So I'm going to start with the formula that I have as delta x equals something. Okay, so you get a little bit. And here, we put a little box around it. So this is what we started with. Okay, so now that we've done that, here's our work. And I'm going to switch up the colors just for the heck of it. So I want delta x equal something. So I'm going to start with what I know, x minus x initial. Okay, so I also know that delta x is equal to something other than that. Turns out that from our equation here in 25, I have a delta x again. So delta x is actually equal to v average times delta t. Or again, because that delta t is really just telling me how much time has gone by, I can rewrite that as just saying v average times my time. Okay, so I now have an expression that I'm relating delta x, v average, and time. Next thing I want to do, I don't have v average in my goals. Okay, so I want to eliminate v average. So what else do I know v average to equal? Well, v average is also equal to v final plus v initial over 2. Okay, so v initial is in my goals in one of my variables, so that's good. But then now I don't have v final, so that's something I'm going to want to eliminate. I'm going to go ahead and scoot this up a little bit. So I want to find what's a way I can substitute or get rid of v final. So without repeating the same equation again and just writing it in terms of v final, I want to find another equation that has a v final in it. And that other equation is my last one. Acceleration is equal to v final minus v initial all over t. What I'm going to do is I'm going to rewrite this. So here, I'll make a little note. I'm going to rewrite. And when I rewrite it, this becomes v final equal v initial plus acceleration times time. Okay, so I've basically gone as far as I can. Now I have v initial, I have acceleration, I have time, I have all the variables that I was looking for, but somehow they're not really connected to each other just yet. So what I want to do is I want to do substitution. I want to take all of this, which equals v, and I'm going to plug it back into this equation for v. So when I do that, this equals v average is going to be equal to v initial plus at plus v initial all over 2. So you see how the first v initial plus at comes from down here, comes from that final velocity. So we're replacing that. And then I still have to have v initial over 2 is the second part of that. So there we go. Next I want to do, we'll switch colors again here, is take all of this and substitute that into where I know is equal to v average. So now I can write that delta x equals v average. Well, v average is really all of this stuff. So it's v initial plus a t plus v initial over 2, let me just put that in parentheses for right now, times t. Okay, so if I look at what my goals were, I want delta x, I want a, I want v initial, and I want t. The number 2, that's just fine. Okay, that's just a constant. So I now want to take this expression and simplify. So I'm going to put a big box on this, and we're going to work our way sideways a little more, and we're going to say simplify. Okay, so to simplify this, I get delta x equals, I can combine my v initial and my v initial, put those two together, so 2 v initials plus acceleration times time, all that divided by 2, still going to multiply across by t. So let's do this one step at a time, and hopefully as you warm up with your algebra skills, this will go faster and faster. Okay, so this can be rewritten as delta x equals v initial plus 1/2 acceleration times time, and then all that times t. So one last time, delta x equals v initial times t, so now I'm distributing the t, plus 1/2 a t squared. And it turns out this is our expression. This is the answer to the question on slide 38. But that doesn't do the numbers, okay? So this is the expression. This is the most powerful answer, okay? But if you want to throw in your numbers, to do that with numbers now, we can say, okay, well, what was my v initial? I'm going to say delta x equals, v initial was 0, because it started from rest, times t. Well, it doesn't really matter what the t is, so we're going to say 0 times t, and that's going to go away to 0, plus 1/2. Acceleration is 5 meters per second squared, times time. Time was 10 seconds, we will throw it in here, squared. Okay, so remember when you are squaring something, scoot this up a little bit, that we're going to have 0 for the first component, and 1/2 squared. 10 seconds squared is actually 100, and then seconds squared. So the units get squared as well as the number. You have to distribute the square to both components inside the parentheses. So now I can just go ahead and do a little bit of arithmetic. So we get delta x equals 250. And if I look at my units, I get meters per second squared times second squared. So this cancels with this, and I'm left with the units of just meters, which makes sense because I'm looking at how far, what's my distance, or in this case, what's my displacement. And that is going to be our final answer for this problem. Thank you for joining me, and I'll see you in the next one.